Hello and welcome to the Water Loss Specialist Group Webinar Series 2025. Today we're very lucky. We have Lameck Dube and we have James Howard, and they're going to be sharing with us a couple of presentations, a couple of case studies based on work that they've done in Africa, in Malawi and in Uganda. I'm hoping it'll be very useful. I'm sure it absolutely will on there. So Lameck, he looks after non-revenue water. So again, he's going to give us a little bit of background. If you could give us a bit of background, Lameck, to what you do, just 30 seconds. And then he's going to be doing a 10, 15-minute presentation. After that, we'll hear from James Howard, who is at Welsh Water, the largest water utility company in Wales. And again, he looks after leakage in Wales. So again, he'll give us just a little bit of background of what he does. And then he's going to be showing us about an interesting project that he did in Uganda. If you've got any questions, please put them in the chat and we'll ask the questions after both presentations on there. So please do put those in the chat and make it available for everybody when you do it in the chat, just so we can make sure that it's just easier to follow that way on there. So Lameck, if everybody else wants to go on mute, Lameck, if you would come off mute and if you would like to kind of introduce yourself, and then we can go from there.
All right, thank you so much, Mike. My name is Lameck Dube. My name is Lameck Dube from Africa, Malawi. I don't know if you have heard about Malawi. I don't know if you have been to Malawi. Most of you, I don't know. But I work as the assistant Nalnevi water officer, physical loss. Now my colleague has been transferred to the other zone, so now I'm working as a physical loss officer. So that's a little bit of my background. My work involves analyzing, doing the analysis on the DMWs, analyzing how they trend in terms of flow measurements, in terms of pressure management. So our organization is divided into 3 zones. We have got the northern zone, southern zone, and the central zone. So in these zones, we have got the zone managers, then the distribution engineer. So if the distribution engineer have compiled their reports, they send to the Lilongwe Water division. So there we do the analysis, the intervention that we can do, and they recommend some other activities that they can do in order to reduce the Lilongwe Water. So this case study we just based on what we did in one of our DMWs, where we had a project funded by Japanese. So this project was looking at they were building the capacity how to manage Lilongwe Water, strengthening our capacity how to manage Lilongwe Water, at least at the very small figures. So this we analyzed the activities that we did. So finally we came to a point whereby I'm going to present on the volumetric measurements, how these volumetric measurements are effective in order to pinpoint the underground leakages. Yes. So that's a little bit background, but I have not yet started presenting my presentation. I don't know if I can start now. Yes.
I'm just trying to move on to the next slide. Sorry.
Yes, please go to the next slide. So this is the outline of the presentation. I'll give a little bit of background of our organization and the activities that are happening. Then also I'll talk about the main objective of the study, then the methodologies that we followed to understand the study. Then also discuss about the findings and the results, and I'll conclude and make some very few recommendations. Next slide, please. So Malawi, like all other sub-Saharan African region countries, our greatest challenge is Lilongwe Water. The figures for Lilongwe Water are very high. This is our problem. Other things we can manage, but Lilongwe Water is still our biggest challenge. So in our organization, NRW involves around 40, sometimes 30, 33 acres. Yeah, so the physical loss 25% and also the commercial loss 15%. The interventions are being implemented to manage both the physical and the commercial losses. So most of the physical losses emanate from the visible leakages and also underground leakages, visible and invisible leakages. So this, if you combine all of them, they make the physical losses. So the method, the acoustic methods are limited in most of the areas because our pipes here in Africa are laid maybe not in paved surfaces like the other countries they do. So you can see the picture there. So that's how the situation is. We don't lay our pipes in paved surface. Sometimes it can be in the bush, sometimes in the maize field. So to detect the underground leakages, it becomes very challenging. So this study we did to assess. We can go to another slide. Next slide. Yeah, so the main objective of the study is just to assess the effectiveness of volumetric leak detection survey so that we can be using these methods in our distribution system to detect the underground leakages. Next. Yeah, so this slide just gives the methodology of how we conduct this study. So what we did, the other picture you see to your right is the DMA that we are doing this study. So the DMA, this was pilot DMA. So this DMA was combined. You can see that this is the MWE 121. Then we had the MWE 12. That's why you are seeing the subzone that are starting from 4, 5, 6. The other subzones are in the MWE 1, 2, which is 1, 2, 3. So we did our study in the MWE 1, 2, 1. So to your left, you see that these are just steps that we did to do this volumetric study. When we are doing this, we make sure that the DMA is hydraulically closed, is hydraulically manageable. When I say hydraulically manageable, we mean that we can confirm that all the boundary of this DMA, or if you isolate this DMA, it should be hydraulically closed. It should not be, for instance, if you want to do the zero pressure test, for instance, you want to check if this DMA is hydraulic, if you close at the back meter, we should not have water inside the DMA. So we understand that this DMA is hydraulically closed. So we did this, we confirmed everything is okay. And also we confirmed that these subzones are also hydraulically closed. So we closed it step by step. We closed all the subzones to make sure that they are not getting water from the other subzone. So this is what we did. And also we did the minimum night flow measurement and step test. On this one, we are measuring the flows during the night, where we understand that everybody is not using water at this point in time. Then we did step by step. We cross subzone number 4, we cross subzone number 5, and then cross subzone number 6 to understand how much is going to subzone, how much water is going to subzone number 4, how much water is going to subzone number 5, how much water is going to subzone number 5. So this assists us to identify where the bigger volumes are being recorded. So after that, this will assist us to prioritize, not just to do the leak detection anyhow, but to prioritize that. I think this section, for instance, subzone number 4, maybe subzone number 5, maybe subzone number 6. This will assist that this section is where we can now prioritize our leak detection. Then we do the excavation to identify the point where we can now clamp our meters, flow meters. Then we do the flow measurements. then we analyze the gas, and now we start the pinpointing work, chasing the leakages and repairing. Next slide. Next. Yes, so I'm continuing with the methodologies. On the first, we do the minimum night flow. After after subzoning, then we did our first minimum night flow to understand how much water is going to respective subzones. So after doing the minimum night flow, we understand that in subzone number 4, that's where we are recording the bigger flow. Then we prioritize that the subzone number 4 is where we're going to do our leakage detection activities. Then we did our leak detection activities in subzone number 4. Then after we did the activities in subzone number 4, the invisible leakages activities. We repaired all the leakages, and now we say that I think we have done we can manage now. Then we come again and do the second minimum night flow. After that, all the activities, then we say, let's go now to measure the minimum night flow again, because these activities we're hoping that we are going to manage at the leakages. So then we went back in the same using the same procedure, the minimum night flow measurement. Then we saw that instead for the flow, the minimum night flow to reduce, we found that it increased from 5.79 cubic meter per hour to 9.79 cubic meter per hour. That's our subzone. We already applied subzone number 4. So that's how we managed. The next slide. Yeah, so these were our findings. We realized that in subzone number 4, we're having the bigger flows. Now we went to check. Now we use the volumetric survey now to measure line by line to understand where the bigger flow is going. Then we found that in this particular subzone, we found that we had an underground leakage. So the picture in your left is showing the leakage that we found. After doing all the activities, after all doing the visible leakage activities and repair works, we realized that the flow is still big. What's happening? Then we start now digging line by line, line by line, line by line. Then we measure this particular line, we found that the flow is too high. Then we understand, we chased all the line. Then after chasing, we found that there was a line, it was just at the end, the line was just, the pipe was just faulty, and it was leaking all days, night and day, night and day. Then we did our repairs on this particular line. After doing the repair for this one, we went again and do the minimum night flow. We found that it has dropped. So we realized that this was the one that it was taking a lot of water, because it was just leaking. It was just an open pipe, like a hose pipe. So it was just going to the drain. So we found that the minimum night flow has now dropped from 9.79 to 6.53. Yeah, so the next slide. Yeah, so after the discussion now, let me conclude. Identification, this activity assists in identifying the small leakages, even if you can, those that the leakage that you cannot detect, the small leakages. So this method assisted us to detect the leakages that we did not even saw it during the physical the visible leak detection exercise. So this one is very useful because it helps to identify even the small leakages that you cannot detect. It's also a real-time detection capacity. this one prompts us to make the collective action and minimize the potential of leak and damage. It's highly precise measurements technique. The volumetric survey offers high, accurate, and precise measurement technique, ensuring reliable leak detection. It's a very comprehensive coverage of leak detection. Volumetric leak measurement survey should be considered as an effective method for undergrounding leak because it measures even the flows that you cannot detect during the visible leak detection. Yeah, next slide. Yeah, so this just showing the picture that is revenue and non-revenue. So NRW is a big challenge to address. Yeah, taking business as usual will not fix it. Thank you so much for your attention. Next slide is, I think, is just saying thank you so much for your attention.
Thank you, Lameck. That's a wonderful case study, and that's a really good example that we can give to new technicians or people that have been in the industry for a while of kind of breaking down your zone into different sectors, breaking it down into DMAs and subsectors. That's a really excellent, and we've got some questions about that afterwards. So I've got some questions. If anybody's got any questions, please write them in the chat. We're going to move straight forward onto a slightly different project now, but again, metering being a real key part of it. We're going to go on to James Howard. And if you could just introduce yourself, James, and give us a bit of background about your project and take us through it.
Thank you, Michael. And thank you for the invite to speak today. My name is James Howard, and I'm a Leakage Optimisation Manager at Welsh Water. My overarching remit at Welsh Water is around the targeting and reporting of leakage. And I mainly work on projects which feed into the water balance, so around leakage, metering, pretty much source to tap. So the topic I'm going to speak about today is customer meter performance, or micrometers as they're referred to sometimes in Africa, and the potential impact on revenue and non-revenue water. So I'll run through a bit of background quickly around the overall project, and then I'll go into the specific study. So next slide. So the project that I've been involved with in Africa is funded by the EU, the European Union, and it's managed by the UN Habitat's GWOPA program, which is the Global Water Operator Partnership. The GWOPA program focuses on supporting water operator partnerships across Africa, Asia, and Latin America, with the goal of improving water and sanitation services through peer support and capacity building. This specific program is a partnership between Welsh Water, the Eastern Umbrella in Uganda, and WaterAid. The aim is to help the Eastern Umbrella to transform 3 schemes in Eastern Uganda, Buyende, Namatumba, and Namayingo, into best practice models of sustainable water operations. These schemes will then be used to benchmark other schemes both in the region and across Uganda. Next slide. So as part of the project, there are key result areas and cross-cutting areas. I'll call out a few of the key areas of the project which I've been involved with. So improved asset management. This will focus on improving asset management data collection, processes, and information systems. Non-revenue water, leak detection, and stores management. Improved water supply availability and reliability. This will focus on improving production processes and water quality compliance. Water quality testing, water safety planning, energy efficiency, and water demand management. Strengthened equity and social inclusion will focus on strengthening accountability mechanisms that deliver inclusive, sustainable, universal access to water, sanitation, and hygiene. And the number 4 that I wanted to call out, strengthened customer centeredness. This will focus on non-revenue water reduction due to domestic and commercial losses, increasing understanding of the customer base, customer relationship management systems, and sustainable management models for public sanitation. Next slide. So got a few photos when they come through. So just for background, some typical scenes in rural Uganda. The photo on the center is a typical shallow well, which was used by individuals that don't have mains water. They're sometimes referred to as shadoofs, and they are shallow wells, and they're abstracted by using basically a container on a string. And the risk around those is obviously contamination from surface water and latrines which are sited nearby. You'll see the yellow jerry cans, which are pretty much everywhere in Uganda, and you often see women and children walking long distances across roads to fetch water. In terms of the piped water system, the bottom right two photos show a typical arrangement. The one in the middle right is a water reseller. So there's a number of taps which are fed via a meter, and then a reseller, usually a small shop, will charge consumers for filling containers. And then the bottom right is a typical private standpipe, which has an above ground meter and then a tap, which is then used for filling containers. Small stat for Uganda is 1 cubic meter of water within this region costs around 3,014 Uganda shillings, which is about 63 pence per meter cubed. And the average consumption is about 4.4 cubic meters per month per connection. Next slide. So a couple of photos from some of the fieldwork that we've carried out as part of the partnership. Photos show some water quality testing training and some leakage detection training being done on site. And the top right is the start of network digitization. That's a hand-drawn map, but as part of the project, we've fully digitized all of the zones and created a GIS system through M-Water. Next slide. So on the first visit to Uganda, one key observation that we made was the variety of different types and ages and condition of customer metering. So on the first visit, we took the opportunity to proactively remove a sample of meters and get them tested back in the UK. The aim was to investigate performance and suitability of current revenue meters and understand the potential impact on revenue and the water balance. And as an output, we wanted to provide guidance on the associated apparent loss estimates, meter reading, meter inspection, and meter testing activity, and to inform future meter specification. Next slide. So going into the testing, there were 4 main tests and assessments that we wanted to carry out. The first one was a standard range of tests recommended in BS 5728, but with additional test points added to gain a detailed picture of accuracy across extended flow range and water use scenarios. Number 2 was to understand the MER associated with water container filling scenarios, because the majority of the rural supplies comprise of an above ground tap and standpipe, which is used for filling containers. So we were keen to understand the meter performance under those scenarios. The third test was an assessment of the starting and stopping flow rates, again to understand the impact of small leaks or container filling at low flow rates. And number 4 was a specific assessment of the standpipe arrangement to understand if the 90-degree bends near the meter have an impact on performance. So the testing was carried out at the WRC facility in Swindon in England in the UK, and we used their small testing rig, which is UCAS accredited and uses a calibrated weighing scale system as a reference measurement. Next slide. So as mentioned in the previous slide, we removed a sample of in-service meters. All of the meters that we removed were of multi-jet or single-jet type and were a mix of wet and dry register types. All meters were either Class B or Class 2 specification. Upon visual inspection of the meters that we removed, it became clear that only a small proportion of the meters actually carried any type approval markings. One of the multi-jet meters had CE and M marks, which show that the meter had been certified as meeting the requirements of the European Measurement Institution Directive and had been approved for revenue use in Europe. The M mark showed that it would have been verified before leaving the factory. The only other meter was a single jet meter, which had a type approval number and an initial verification mark. All other meters did not contain those type approvals. Next slide. So going into the testing, apologies for the busy slide, but I'll try and summarize it. The first test we did was on the standard test points recommended in BS 5728, but with extended low flow and high flow test points to cover the full Class B and Class 2 specification. We did use the in-service limits set out in Annex C of ISO 4064 for scoring the meters. Specifically, the tolerances state that in-service meters should comply with plus or minus 10% between the Qmin and the QT transitional, and plus or minus 4% between QT and Qmax. In terms of results, although all meters were within the expanded error limits at medium flow rates, only 2 of the meters that we tested were fully within the expanded error limits over the full range of flows. And I've put some red dots on the table just to highlight where the worst performance is. And you can see that the worst performance is clustered around the very low flow rates and the very high flow rates. And all of the meters tested did seem to suffer from under registration at both the low flow rates and high flow rates. One key observation that we made as part of the initial test was the significant under-recording that we saw at very high flow rates, and we deemed that that's most likely due to the slippage in the magnetic link between the measurement chamber and the register of the meter. Another possible cause is stalling of the impeller within the meter caused by an imbalance of the impeller or turbulence within the meter. Next slide. So this slide shows a few samples of the graphical results. You can see that the dotted line, which is T-shaped, shows the in-service limit suggested in ISO 4064. The solid line shows the actual performance of the meter. So you can clearly see the negative error at the low flow rates and the high flow rates. Next slide. So the next test was around the container filling scenarios. The aim of the test was to show the volume of under registration associated with a real world example of container filling. The table shows estimates of the percentage under registration associated with a container of 10 litres being filled in over a different time period and therefore different flow rates. We chose a representative sample of meters for this test. We didn't test every single meter under this scenario. So in terms of the results, one of the meters, meter number 1, performed poorly at high flow rates and was outside of the extended test tolerance for all flow rates above 360 litres per hour. The red dots in the table highlight the worst areas outside of the extended error limits. So this was quite interesting, and we considered the impact of this around container filling. And although it would be unexpected to see flow rates as high as 1,500 litres per hour being used for container filling due to splashing and uncontrolled nature of that type of flow rate, it is conceivable that we would have flow rates of around 750 litres per hour. Therefore, there is a risk that under those specific scenarios, meters of that type would significantly under-record the volume associated with container filling. And on the next slide, we also looked at the starting and stopping flow rates of the meters. So the test rig was run at an increasing flow rate until the meter started to record flow, and then again at a decreasing flow rate to observe when the meter stopped recording completely. In the results, we could see the standout was meter number 4, which was one of the multi-jet Class B meters, and it is not sensitive to low flow rates at around 18 to 19 litres per hour, whereas the meter number 10, which was a newer Class 2 multi-jet meter, was far more sensitive. And this is consistent with meter 10 having a lower minimum flow rate because it's a newer meter and is accredited to a more stringent standard. So the main insight that we took from this was that there is a risk around small leaks at the faucet being under-recorded, and also potentially container filling, which is carried out at very low flow rates, would not be registered. Next slide. So the last test that we did was around a mocked up standpipe arrangement to replicate the arrangement that you see in rural Uganda. So the top right shows the a typical standpipe arrangement, showing the meter and then above ground tap. And the bottom right shows the simulated standpipe arrangement that WRC fabricated on their rig. So in summary, we found that the standpipe configuration did have an impact on the error curves for all meters tested. However, the impact was not consistent for all meters. For meter number 4, the results were consistent with the initial testing, so the standpipe made no difference. For meter number 8, the errors have increased in the negative direction. However, it's not that significant, and they've remained within the expanded limits for in-service meters. However, for meter number 10, the error curve has moved upwards and the performance has improved in the low to mid range. So the standpipe arrangement actually improved the error at those low to mid ranges, and the errors are well within the expanded limits for in-service meters. However, for that meter, meter number 10, at the high test point flows, the under-registration had increased significantly, and the meter recorded very little consumption at those higher flow rates. So in conclusion, it was very clear that the turbulence caused by the 90-degree bends can have an impact on different meters in different ways, and the impact is not consistent. Next slide. So the next 2 slides were not specifically part of the testing that we carried out at WRC, but it was from observations and investigation as part of the fieldwork on site. And the first one is around meter tampering. So whilst on the ground, I had the opportunity to speak to some plumbers and site workers, and we had the conversation around the different ways that meters can be tampered with and what they'd actually seen on the ground. So these can include temporary removal of the meter by a customer, a hidden bypass, meter reversal, so physically a meter being removed rotated, put back in, spun backwards, and then reversed again to cause the meter to under-record. Another type is physical mechanism removal or modification. So on wet type impeller and register meters, there was evidence that customer had physically removed the entire mechanism for a period of time and then reinserted it at a later date. Another type is magnetic interference and also physical interference. So one key example that we found in the image shown was where a dry register type meter had a small hole drilled in the screen and a pin inserted to stop the register from turning. So I've used these two slides on the ground to increase the awareness for all scheme staff involved in meter reading activity to increase the vigilance and record keeping of this sort of activity. Next slide. So the second area was exploitation. So again, from insight gained on the ground, especially on the very old basic types of meter, scheme staff did note that they had observed this sort of exploitation behavior occurring, whereby containers were filled at a very low flow rate, below that of the starting flow rate of the meter. And secondly, at a very high flow rate whilst observing the rotational stop of the meter. So in terms of the key action around this, it led us to having a key recommendation that future procurement should concentrate on good quality meters which have been verified to meet international standards and which have individual verification from the factory, and specifically the procurement of meters with good high turndown ratios, which allow registration of those both high and low flows. Next slide, please. So in closing, in terms of conclusions and recommendations, from the initial testing, we did find that only 2 of the meters tested were within the expanded limits over their operating range. Although most of the meters were within plus or minus 4% in a limited part of their range in the middle of the section. All of the meters tested tended to under-record, which is typical of wear in mechanical meters. Under-recording was most significant at low flows, less than 30 litres per hour, and also at very high flows. The latter most likely being, as we discussed earlier, due to slippage in the magnetic link between the rotor and the register, or turbulence within the impeller itself. So from the test results, although it was a limited sample, it is likely that consumption is being under-recorded as a whole. Although the testing was limited, an estimate of an under-registration was made of around 23%, and that was based on the container filling scenario. Obviously, more testing is required to bolster the sample and to understand the full meter estate and the levels of under-registration on different types of meters. Meter tampering, exploitation, and failure regularly occur on the ground, but detailed records did not exist in all cases. Next slide. So high-level recommendations and actions. So in order to improve estimates of non-revenue water and ultimately reduce water loss, it's necessary to have good understanding of the amount of water being used. Reliable and accurate metering is essential to this. So there are a number of recommendations and actions that we've set out and enacted as part of the project. Firstly, meters should be procured to a good standard and a recognized international standard, such as ISO 4064, and should carry individual meter verification evidence from the factory to ensure that the meters are working as expected before they're installed. The sensitivity to low flow rates was quite varied across the meters. So as a future specification, a minimum recommended standard has been agreed of a Q3 2.5 meters cubed per hour meter with a turn down of at least R160 will be considered as part of future procurement types. Also, the move to dry registers in all cases will be used because it was noted that because of the above ground location, buildup of algae can occur in wet register meters, which obviously from a water quality perspective and a meter performance perspective is not prudent. So the next area was to ensure that any new meter specification is tested specifically on the standpipe arrangement to ensure that there aren't any nuances with that specific meter which could cause under-registration in turbulent flow conditions associated with the standpipe arrangement. We've also written a standard operating instruction for scheme staff regarding meter installation to ensure consistent and reliable installation practices. And as I said on the earlier slides, the tampering and exploitation awareness training has been rolled out to all scheme staff involved in meter reading activity, and meter reading records have been bolstered with data fields so that data can be captured to support meter replacement programs in the future. So as simple as noting whether a reading is actual or estimated, and also the condition of the meter at the time of being read. So for example, is it functioning? Is it faulty? Is it clogged? Is it tampered? And the last recommendation is implementing a level of in situ meter checks and testing in the field to ensure that basic performance tests can be carried out. And I think that is it. And in the appendix is the recommendation for those in situ tests.
Thank you, James. We really appreciate that and for your time and putting that together on there. So we've got time for some questions. I'm going to start with Lameck first. And please write your questions in the chat. So Lameck, you've got some really good success there. You found a fair bit of leakage there by doing kind of your step test and using the metering. Is there an ambition to do more, to go forward and do it in different parts of Malawi?
Yes, there's an ambition, and that's what we are doing now. We are transferring this knowledge to the other zones, as I already indicated that we have 3 zones. So we are prioritizing some demos. At the moment, we have got 30 demos where we are doing these activities. So we are doing both physical and the commercial activities. When it comes to physical losses, we are also using this volumetric measurement survey to understand the underground leakages. After repairing the visible leakages, then now if we see that the volume, the volumeter is not dropping, we understand that maybe it's the underground leakages. So we also use this method to understand the underground leakages in all our DMAs. As of now, we have got 30 DMAs where we are prioritizing to do these activities. Yeah, so I saw the 2 questions in.
Yep. Okay, let's take the first one. So the first one is about the acoustic method and says, why is it limited to paved areas? His understanding is from Paul that you can use it on that you can use ground microphones and acoustic rods and everything on unpaved areas. What are your thoughts on that, Lameck?
All right, on that one, our observation is that these acoustic leak detection equipments for instance, what he has mentioned, ground microphone, the listening sticks, they work best in a paved surface. Here in Africa or in Malawi, it becomes very difficult to use for instance, the ground microphone to detect the underground leakages because the surface is just not paved. For instance, it works better on the concrete because the sound of the leakage is well transferred in a paved surface, unlike the unpaved surface. For instance, maybe a road, and not a road maybe in a maize field, you can't use the ground microphone, or you can't listen carefully and detect. And if you want to detect the leakages using the ground microphone or the listening sticks on unpaved surface, then you need to have the special skills that you should use. Otherwise, we recommend that this acoustic methods works better in a paved surface because anyone can easily identify, can easily capture even the smallest sound of the leakage on a paved surface, unlike non-paved surface. Yeah, so that's
Okay.
what we observed here. Yes.
Okay, brilliant. Thank you. And then on the next question, Mike wants to ask, how did you synchronize the readings from water residential meters and the subzone meters?
Yeah, on this one, because the GME that we used, we had very few customers, so it was easy for us to know that this is the consumption from the meter and this is the leakage. It was able for us to detect that this is consumption, this is not the consumption, because how the demo was demarcated. So we are able to see that this is the consumption for this demo, and this is not the consumption. So it was easy for us to synchronize these two. Yeah, thank you so much, Mike.
Yeah, absolutely. And you were doing it at night, weren't you? You were looking at a lot of the meter reads where people are hopefully asleep and in their bed and not using
Yeah,
water.
yeah,
Okay,
yeah.
right.
Thank you.
Yeah, thank you, Lameck. James, we've got a few questions for you on the metering. Could you confirm what's the most suitable technology? Is it wet or dry?
So what we did find when we were on the ground was that because the meters are above ground, pretty much on the equator, it's quite a challenging environmental condition for water meters. They get a lot of UV, get a lot of sunlight, they heat up in the sun. So we did find that the fully wet meters did have a buildup of algae in a lot of cases, which obviously not good from water quality and meter registration perspective. So the newer specification of meters is to use a dry register meter, so there isn't that risk associated with algae buildup. So that's the specification that's been recommended. If that's the question, is that around the registers?
Yeah, excellent. I'd never thought about that. So here's another question. How did you make sure that the water's kept wet when you took them back to the...
Yeah, yeah. So that was interesting getting those meters through customs. Uh, so what we did was when we had them removed, we put as much water in them as possible, and then thoroughly taped the inlets and outlets, and then um, double bagged them, and then put them in a protective sack in another sack in a box so that they weren't damaged during transit or dried out. So we tried as best we could. They were still wet and in good condition when they arrived at the test house. So we did everything we could.
Okay. And then the final question we got from Paul. So on your presentation, James, what is the recommended meter installation arrangements and meter sizing to eliminate registration errors?
So I think the problem is that in Uganda, they're currently limited to the arrangement that they use by design. So it's quite an innovative solution, the standpipe arrangement, because it uses minimal fittings and it keeps the new connection price low, because that's a big barrier to entry for new customers to piped water supply systems, is the initial new connection charge. So the arrangement is the minimum viable solution of providing a metered connection with a tap. So that standpipe is what is currently used. In terms of ensuring that any installation doesn't impact on meter performance, two factors. One is obviously checking and verifying the performance of the meter in the proposed installation condition. So for example, does the manufacturer recommend a number of straight diameters of pipe before and after the meter? So, for example, the equivalent of 5 diameters of pipe upstream and downstream from the meter. So check with the manufacturer to understand the recommendations for the meter, and secondly, do some tests as well. So as we showed in the standpipe arrangement, some meters were unaffected by the 90-degree bends, but some meters were affected. It's not consistent. It depends on the meter make, model, and type in terms of how they're impacted. And in terms of meter size, again, the standard domestic meter size in the UK and internationally is generally a DN 15 millimeter meter, and that's generally standard and is seen to having at that size the best mix of low flow performance but higher flow capacity in a domestic environment. For commercial meters, obviously that's a different scenario, and meter sizing for commercial customers should always be considered based on the demand downstream to ensure that the majority of demand and flow is sitting within the limits of where the meter is accurate.
Okay, brilliant. And one really quick question before we come to Lameck. What's the typical pressure in the system, James? Do you know what the typical pressure is?
So on the test rig we used, I think 1.5 bar. In Uganda, the pressure does vary. The rural schemes are generally gravity fed, not pumped. So they comprise of a borehole or spring, which is pumped up to a high level tank, some basic treatment, usually chlorine dosing, and then it gravitates from that high level tank into the network. So there can be varying pressure, I think between generally 1 bar and 5 bar we saw in the rural schemes, but it depends on the configuration and the topography. There was no pressure management in the rural schemes, but it is something that we've done some basic training on for awareness when they start to expand schemes to think about the management of pressure.
Brilliant. And this is the final question, and then we need to finish. Lameck, what was the non-revenue water percentage you had before and after you did this project? And have you got a goal of where you want to get non-revenue water to as a percentage? Lameck, are you able to hear us? We're just wondering what the percentage of NRW was, kind of before
Yes,
and after.
yes, I'm able to hear you. I'm trying to open a DMA bar sheet so that I can give you the real figures. Yeah. So yes, we are the volume, even the percentage improved, because at the initial stage of the activity we had the 53% as in non-living in this particular DMA, but after the exercise it dropped to 20% of the non-living in this particular DMA. Yes, we are trying to enroll to all the demos in our distribution system. And that's what we are planning now, because it starts some activity, but as I already indicated that at this point in time we have prioritized 30 demos. These demos have got high level water. Yeah, so we are prioritizing in each zone. Yeah, so we got the 30 demos in total, because in our distribution system we have got the 119 demos which are balancing. So at this moment we are now targeting 30 as the starting point, whereby we are doing all the activities, the commercial activities and also the physical activities. So in physical activities, we are using the same method of volumetric measurements. Yeah, so thank you.
Brilliant. And do you know if you're losing lots of water between the supply point and the DMAs? Do you know how
Come
long is
again?
that? Do you know? Do you know if you're
Come again?
losing much water between the supply where you abstract the water and where?
You mean the overall level water?
Okay. All right.
Oh,
We're coming up. We're coming up to the end now, so we'd like to thank Lameck for his time today. Thank you, James, for your time. It's been a really interesting presentation. We do have another presentation coming up in a few weeks' time on water loss. So please join us again. And thank you, Lameck. Thank you, James. We really appreciate your time today. And everyone, go have a good Friday. Okay. See you. Bye-bye.
thank you
Thanks
so
all.
much. I hope you give us the link when we are going to have another webinar.